All right, now everybody, we are going to continue on with the fundamental theorem of calculus today. Fundamental theorem of calculus part 2 is a very big skill, so really what I want you to do is practice on it. We're not going to have a very long video today, but there should be a lot of practice problems that you could find from a variety of resources for this. So let's look at the do now here real quick. We're bringing it back to antiderivatives. When you're calculating antiderivatives, you should be just talking about that that rule sheet that we had from chapter 3. You want to read that rule sheet in the reverse fashion. These are the derivatives of the function. We want to calculate what the antiderivative is. So you want to be listing that as capital F of x is equal to, and then just think, what gives me a derivative of 0? Well, that's any constant. Remember when we talked about anti-differentiation, we talked about having that plus c on there, right? So here, like thinking of what gives us a derivative of negative 1 over 1 plus x squared, well, I see that that's in the fractional Pythagorean form. I'm going to look at my inverse trig rules. 1 over x, that's a very basic rule that we have here. Secant squared draws my attention to the trig rules. Down here, ooh man, that's going to be a very big issue. A lot of times people struggle with anti-differentiating with power rules. So I'm just going to do a little bit of scratch work here to help us out on number 5. If we're talking about the derivative of x to the nth, we have n x to the n minus 1. So we multiply by our old exponent and subtract by our old exponent to get our new exponent. Now what we want is we have, let's make this a separate color just to keep it separated here. We have the function is equal to x to the nth. That's going to imply that its antiderivative, we need to do the opposite of everything we did for the differentiation. So instead of subtracting 1 from our exponent, we need to, opposite of subtract, we need to add 1. So this is going to be x to the n plus 1. And then opposite of multiplying, we need to divide off. Here, we multiplied on our old exponent. Here, we're going to divide off our new exponent. So if you're looking for a power rule for anti-differentiation, x to the n plus 1 divided by n plus 1. If I'm looking at number 5, I mean, I really wanted to spell out the work here. F of x is equal to x to the negative 2/3 plus 1 divided by negative 2/3 plus 1. And then looking at that, oh, plus c. Almost forgot my plus c. Looking at that, I look at what negative 2/3 plus 1 is. That's positive 1/3. So I have x to the 1/3 divided by 1/3 is the same thing as 3. Multiplied by 3. I mean, not just 3. So maybe pause this, come back to it. I will point out that 6 is probably the hardest one up here. I don't feel like explaining that right now because it's something called u substitution. Number 7, since we have the derivative of 3 to the x is 3 to the x ln of x, ln of 3, we would have to divide by that ln of 3. Just thinking of common mistakes that people make, I always see people screwing up number 3, determining what the antiderivative of 1 over x is. That's a huge one that people often screw up. So again, that's what your do now would have been if you were in class. And now to look at fundamental theorem calculus part 2. If f is continuous at every point of the closed interval from a to b, and if capital F is any antiderivative of f on the interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Now I do want to point out some things here. First off, since we're talking about capital F of a, or sorry, capital F of b minus capital F of a, it is in the theorem, but note that these are our anti-derivatives. So capital F means anti-derivatives. Always make sure you anti-differentiate and then evaluate at the upper. subtract evaluating at the lower. And I will try to give you the tools to be able to do that with very, well, as long as you show your work, it should be easy to keep track of it. I do also want to point out that on our do now, we had to include the plus C. We now no longer have to include the plus C. I will show you that here in just 1 second. But first, I do want to show you some direct results of the Fundamental Theorem of Calculus Part 2, but you should definitely have this in your notes. It is also called the integral evaluation theorem because it is how we evaluate definite integrals. Now looking here, the direct results of the Fundamental Theorem of Calculus Part 2 is that any definite integral of any continuous function f can be calculated without taking limits, without calculating Riemann sums, and often without effort, so long as an antiderivative of f can be found. So like for the past couple of sections, we've been saying to get the best answer possible, to get the exact answer, you have to use infinite rectangles for this, which would be a pain in the butt to try to calculate a Riemann sum with infinite rectangles. Now we know that we don't have to use a RAM as long as we can find the antiderivative, which sometimes can be tricky. Now there is something that I wanted to show you guys here, and that is why the plus C doesn't matter. While I'm doing that, I'm going to try to show you some notation that we use for calculating our definite integrals. So let's just pretend that we are trying to find the integral from a to b of f of x dx. Now I know that in order to find my antiderivative, or my integral, I need to calculate my antiderivative. So down here, below here, I'm going to say lowercase f of x is equal to capital F of x. The actual antiderivative would have to include my plus c, right? So I'm going to have plus c. Now I am going to point out that if I calculate the antiderivative of f, the capital F is going to have the same c if I'm talking about just one function here. So no matter where I write down c, it's going to be the exact same c, all right? So now for the notation that we use for calculating our definite integrals. The notation that we use is first, in the boxy brackets, and I think I showed you this the other day, inside of some boxy looking bracket things, we just calculate the antiderivative. So that's the notation that we use. I will point out that some people use, instead of these boxy brackets, they use that evaluation bar at the end of the function, just like when we were calculating derivatives. I only tell you that because I don't want you to get confused if you're looking at some other resources and all of a sudden somebody doesn't use these brackets, they just use a solid line at the end. I like the brackets in case I'm calculating multiple definite integrals at once. They behave as grouping symbols to keep the antiderivative by itself. Some people can keep track of that without the grouping symbols, but I'm just not that kind of person. So now what I want to look at here, again, the Fundamental Theorem of Calculus Part 2 says in order to evaluate this, I need to do the antiderivative at the upper, at f of b plus c, minus the antiderivative at the lower. So notice what we have now is I've got capital F of b plus c minus capital F of a plus c. Now if I distribute the minus in the second group of parentheses, I'm going to get capital F of b plus c minus capital F of a minus c. Now way back when I set this up, when I said lowercase f of x implies capital F of x plus c is the antiderivative, we said that the c has to be the same value here, right? So the c has to be the same value. I've got c minus c, those cross off right here. And all of a sudden, we've just got capital F of b minus capital F of a, which is the original Fundamental Theorem of Calculus Part 2. So basically what we're trying to say is capital C doesn't matter when we're doing definite integrals. We only need to worry about that when we're doing just straight up anti-differentiation. I guess I can tell you what those are called if we don't have limits on our integrals. They're called indefinite integrals because they go on indefinitely. And one thing that I did mess up here at the beginning, I did not want to say f of x equals capital F of x plus c. That is just a fallacy. The function does not equal its own derivative except for like e to the x. Ooh, yeah. All right, now let's calculate some antiderivatives. And I might pull up some other examples just to show you that we can actually do this multiple ways. But let's start off with the integral from -1 to 3 of 3x squared plus 1 dx. And whenever I start this off, I like to just copy the integral down just to keep track of what I'm doing. All right, cool. There we go. Now we need to calculate our antiderivative. We're going to put that in some boxy bracket things and not touch our limits for right now. So we need to figure out what's the antiderivative of 3x squared. Some of you might be able to say it right away. Some of you might have to use that rule that I gave you on the do now, where we'd have 3x to the 2 plus 1 divided by 2 plus 1, again using that x to the n plus 1 divided by n plus 1 for the anti-differentiation, plus what gives me a derivative of a constant. We've always been differentiating linears down to just their slopes, so it has a slope of 1, that would be 1x, from -1 to 3. Now here we have some opportunities to simplify stuff. I'm going to keep the boxy brackets just to show the simplifying. Honestly, if I was doing this on my paper, I would jump from this step to what I'm about to write down. But you might need to practice by writing down all the steps right now. I see 3 and divided by 2 plus 1. I know that those cancel off. I know that I've got x cubed plus x in here. Why do I simplify it? Because now I have a bunch of crap that I want to write down. I need to write this down as evaluate at the upper minus evaluate at the lower. So a couple of things that I might throw some caution for you guys at this point. A lot of times when I see errors on this one, I do see people not taking the antiderivative. That's a huge mistake. I also see some people switching up the limits. So they do evaluate at the lower minus evaluate at the upper. It is always the upper limit, 3 cubed plus 3 minus the lower limit, -1 cubed plus -1. And now do whatever arithmetic that you need to do in order to get the final answer. I will say that, again, we know how to use our calculator in order to approximate a definite integral. We'll use that to check to see if our answer is right, but you do not want to just write down integral blah 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 equals and then an answer. I need to see your work. So at the very minimum, I need to see this, 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 and an answer. Of course, there's a lot of work here. What? 27 plus 3, so 30 minus -1 cubed. -1 plus -1 would give me -2. 30 minus -2 would be 32. So again, I will highlight the parts that I need to see on your paper in order to get full credit. Anything more is just making sure that you are keeping track of all of your work correctly. And there you go. Those are the absolute bare minimum things that you need to show me in order to get full credit. Let's pull up my calculator to see if we're right. So you can see, according to the calculator, at least we're in the right ballpark. I mean, it says 32 over here. We calculated 32 by hand. That sounds pretty good for me. Now let's try the second one. You might want to pause the video, maybe try it real quick. While I figure out how to work my computer. There we go. Finally got it. So we got the integral from 0 to 1 of 1/3 e to the x minus x squared dx. I know it looks super, super difficult, but let's see what we can do. So looking here again, we've got integral from 0 to 1 of 1/3 e to the x minus x squared dx. Again, I would not recommend skipping, and in fact, you have to show me this step. I was going to say I would recommend against skipping that step, but I must see that step where you calculate the antiderivative. So I must see the boxy bracket looking things. If you get frustrated with that, okay, fine. But this is just one of those situations where you have to appease the teacher. I'm looking for the antiderivative of 1/3 e to the x. Well, that 1/3 is a constant multiple, so it carries over. Now I need to think of what gives me a derivative of e to the x. Derivative of e to the x, oh, hey, that's the easiest one to remember. It's just e to the x. Minus, over here we've got, let's see, antiderivative of x squared. Again, it's a power rule, so I'm going to have that x to the 2 plus 1 divided by 2 plus 1. In all sincerity, if I was doing this myself on my own paper, I would have skipped to this step, the 1/3 e to the x minus x cubed over 3. With enough practice, you can probably get there, but again, since this is the first time you're doing it, I would recommend putting this step down from 0 to 1. Now in this next step, try not to cut any corners going from here down to the next step. Like right now, I see a corner that I could cut in this, that it is killing me that I'm not gonna cut this corner, but yeah, make sure you keep track of absolutely everything. So what I mean is in this next step, we've got 1/3 e to the, my upper limit was 1. So 1/3 e to the first minus 1 to the cube divided by 3 minus 1/3 e to the lower 0 minus 0 to the cube over 3. Nope, not a boxy bracket. This was a parenthesis. So again, try not to cut any corners when you go there, because there are some things that you can screw up. Like one thing that I've always done that is a mistake, whenever I see a 0, I just blatantly don't write down anything in the minus part. That doesn't work all the time, because sometimes plugging in a 0 yields a number that is not 0. So again, looking here, we just want to evaluate as many things as possible. 1/3 e to the first is just going to be 1/3. That's not how we spell 3. 1/3 e minus 1 cubed is 1, so minus 1/3 minus, now I see this e to the 0th power. I happen to know anything to the 0th power is 1, so I've got minus 1/3. Distribute this in here, so this becomes a plus. 0 cubed is 0, divided by 3 is 0. Alright, cool. I would be alright with you leaving it here, however, it just doesn't look right. 1/3 e minus 2/3 would be my final answer here. And let's pull up my calculator to make sure that we have it right. Now the kind of annoying thing about typing this into our calculator, we have no idea if that's actually the answer that we just got, do we? So we actually have to type in our answer to compare it. So now you can see I have my answer typed in, and look at that, exact same answer. So again, use your calculator not to calculate these, but to check to see if you're in the right ballpark. So I do want to point out that sometimes there are easier methods to do this, but regardless of how you do the problem, you should get the same answer. Like looking over here, the integral, oh, wait a second, I didn't mean to, okay, so this wasn't the example that I meant for it to be. The example that I meant for this one to be, I meant it for it to be the integral from 1 to 7 of x dx. I don't know how I accidentally put that x in there, but let me get rid of it real quick. There, it's like that x was never there. Although I know some of you are going to be annoyed that there's like those little pieces of the x peeking out. There we go. The integral from 1 to 7 of 6 dx. Now looking at this problem, I could do this using the fundamental theorem of calculus part 2. I could do the boxy looking brackets, think what gives me a derivative of 6. What does give me a derivative of 6? Okay, that is 6x from 1 to 7. I can go back and I can figure out what is 6 times 7 minus 6 times 1. Okay, so 6 times 7, 42 minus 6 would give me 36. So it is possible to use this using Fundamental Theorem of Calculus Part 2, but we also have a formula for this. We learned it, two videos ago, where we have the integral from a to b of c is just c times the difference of b minus c. Or we could also look at this geometrically, realizing that the graph of 6 is just a horizontal line at a height of 6 running from 1 up until 7. So there's my function right there, drawing in my limits like we've been doing this chapter, and shading in the area that we're talking about. Again, remembering that the definite integral just means the area under the curve between those two limits. All of a sudden I see that I've got a rectangle. The height of my rectangle is 6. The width of my rectangle is 6. Legitimately, all of this work could be summarized just in 6 times 6 equals 36. So again, that first line is the equivalent amount of work as up here. It's all about just finding out what strategy do you want to use. Again, over here, I can take my antiderivative. What gives me a derivative of 2x? Well, that one's pretty easy for me. I don't know if it is for you, but x squared differentiates down to 2x. And I'm going from 0 to 4. So this is going to be 4 squared minus 0 squared, which would be 16 minus 0. That's just going to give me 16. Alternatively, if I wanted to graph 2x from 0 to 4, I know that I start at 0, 0. This is a line ending at 4, 8. Again, drawing in my limits, starting at 0, ending at 4, I draw my figure, and all of a sudden I have a triangle, a right triangle with a base of 4, a height of 8. Legitimately, this work could also be half of 4 times 8, which is half of 32. It's 16. This will work every single time, as long as you can calculate the derivative or you can recognize a geometric shape. Now, there are certain times when the Fundamental Theorem of Calculus Part 2 does not work, and those cases are where you just don't know what the derivative is. Like here, I don't know. Big, fat, this. No clue what that could be. So I have to look for alternate ways of calculating this definite integral. Now, from a couple of videos ago, we recognize constant minus x squared underneath of a radical is a semicircle with a radius of the square root of this, centered at the origin. So drawing this shape, I happen to know that I go from -2 up to 2, I have a height of 2, and the shape looks like this. Now when I want to calculate this integral is talking about the area of that shaded space. That shaded space is a half circle with a radius of 2. Legitimately, the only way that I know to calculate this definite integral without a calculator is by doing half of the pi r squared. So half of 4 pi would give me just 2 pi. And if I wanted to pull out my calculator, I could show you. You know what? Forget it. I do want to show you. And just to prove to you I get the right answer, 2 pi is equal to whatever the calculator, oh, I see that it's after a little while we can see some difference in these numbers, but that's just added up to your calculator's a dum-dum and it's giving you an approximation. This is the exact answer, 2 pi. This is the approximate answer off after like a 1/1,000,000th. Yeah. That's really all we have for today. There is a practice sheet in the Schoology folder. We will probably work on it tomorrow along with some problems out of the book. But yeah, Oh, dang it, no, we had some other stuff. We gotta find area between the curve. Oh my goodness, I can't believe oh man, I skipped over this part. Ooh, man, I can't believe this. So finding the area between the curve and the x-axis. Alright, so just like everything else, there are multiple ways to calculate the area between the curve and the x-axis. This is the first way, this is the analytical way where you can actually do it without a calculator. So in order to find the area, what we have to remember in calculus, a definite integral is the concept of a signed area. So we've got negativity and we've got positivity. So in order to calculate the area, the first thing that I need to find out is where the function changes from positive to negative, and that's at the zeros of the function. So here, I'm looking for where does x squared minus x minus 6 equal 0. And looking over here, I can see that it's at -2 and 3, but really the whole idea here is to be able to do this without using a calculator, without using a graph here. So we're going to factor this. We'd have x minus 3 times x plus 2 is equal to 0, which we know using the zero product property means either x minus 3 equals 0 or x plus 2 is equal to 0. So there's how analytically we can get x is equal to 3 or x is equal to -2 for our two zeros. Now to calculate the area, what we need to keep in mind is the area changes from positive, or the concept of the area changes from negative to positive or positive to negative at 3 and -2. So basically along this interval that we're working with, between 1 and 4, we need to split this up into two different sub-intervals. We need to talk about the interval from 1 up until we switch signs, and then where we switch signs up until the end of the interval, which is at 4. So we need to take this area right here and add it with this area right here. And the way that we do that, we calculate the area from beginning of the interval, 1, to the 0 that's on this interval. The first 0, well, -2 is not on this interval, but 3 is. So we're going to talk about the integral from 1 to 3 of x squared minus x minus 6 dx, and add to it the area from 3 to 4 of x squared minus x minus 6 dx. Now there is something that I left off of here, and the reason why I left it off there is to show you that if I leave it off, this is a ridiculous thing to do. This now becomes, using additivity, the same thing as the integral from 1 to 4. In order to calculate the actual area, once I've subdivided my interval into positive and negative area, I need to toss out any negativity by taking the absolute value of both of those integrals. Now I'm just going to calculate that integral by hand like I have for all of the other problems today. So here I'm going to have this first one is antiderivative of x squared is going to be that add 1 and divide by my new exponent. Minus integral, antiderivative of x is add 1 to my exponent and divide by my new exponent. Minus antiderivative of a constant is just a linear. So good news. Notice how we had to do that antiderivative for that first interval, and the second interval has the same antiderivative. We've just saved ourselves a little bit of time. This becomes x cubed over 3 minus x squared over 2 minus 6x. And just to emphasize the reason why I did that so fast, I just copied from the first interval, 3 to 4. And now, yes, I do have to be super messy about it. Absolute value of 3 cubed divided by 3 minus 3 squared divided by 2 minus 6 times 3. Again, there I'm just evaluating at the upper, minus evaluate at the lower, 1 cubed thirds minus 1 squared halves minus 6 times 1. And my absolute value bracket, and do the same thing for the next one. I'm going to pause and just fill that out real quick. Alright, so you can see all I've done there was plug in my upper, plug in my lower. Again, we have quantity over here stuck together, quantity over here stuck together. We have to evaluate them individually. I'm going to pause here while I evaluate all of my arithmetic. So again, just emphasizing I was just doing arithmetic there. 3 cubed divided by 3 is 9. 3 squared, 9 halves. 3 times 6, 18, sorry. Distributed my minus throughout here so that I have minus 1/3, plus 1/2, minus 6, absolute value of all of that. Now over here I've got absolute value, 4 cubed is 64, divided by 64 thirds, minus 8, minus 24, all that stuff right up here, 16 halves. Then distributed my minus over here, so I'd have minus 9 plus 9 halves plus 18 over here. Again, looking for just how to combine this stuff. I'm going to pause, maybe do some arithmetic, and come back to you in just 1 second. And in the midst of doing all of my arithmetic, I realized a very tiny mistake that's going to ruin my entire work right here. Right here where I distributed my minus, I forgot to carry it to the 6. So that should be plus 6. That's going to change everything. So, one slip up later and lots of arithmetic later, I have 61/6. I do want to emphasize the hard part of this was not the calculus, which was only done in this step right here. The problem was with the fractions and the keeping track of negatives and positives. If only there was an easier way. If only. But here I do want to summarize how to do that analytically. Again, analytically without a calculator to find the area between the graph of y equals f of x and the x-axis over the interval from a to b analytically without a calculator. 1, partition a to b with the zeros of f. 2, integrate f over each subinterval, and 3, add the absolute values of the integrals. Now, I will point out that that's a pain in the butt to do. Real quick, let me switch over to the other slide and grab that integral. Okay, so I guess by grab that integral, I didn't actually mean grab that integral, I meant grab that function. Because what I want to do right now, real quick, is just graph the function y equals x squared minus x minus 6. Just do that real quick on your calculator on the standard Zoom window. So what you should notice is you have that area underneath the x-axis, just like the graph showed on the last page. Now, what I'm going to do, instead of graphing the function, I'm going to graph the absolute value of that function. So here I'm graphing the absolute value of x squared minus x minus 6. I'm doing it on the same window so that you can see what happens here. Hey, look at that. The function is identical except for the fact that right here I have, instead of the blue part being below the x-axis, I have the red part being above the x-axis. The reason that we have that is because we took the absolute value of each function value, took all your negativity and made it positive. What I'm trying to say here, instead of trying to find the integral of the actual function, I can now find the integral of the absolute value of the function. So here I can find out that my area might be equal to the integral, and again I'm going from 1 to 4 of the absolute value of x squared minus x minus 6 dx. And when I type that into my calculator, let's see what happens. On my home screen, I've got the integral from what did I do here? Okay, I want this one, integral, not summation, from 1 to 4 of the absolute value of x squared
minus x minus 6, exit my absolute value dx. And look at that, 10.166666666, which if I remember what my answer was from the previous problem, 61.6. Look how close they are. If you can just do the integral over the entire interval of the absolute value of the function, you can get the same answer. The shady part about that is you have to use your calculator in order to do it that way. Again, our idea is we want to do it without a calculator. So here's the strategy if you have a calculator at your disposal, just the numerical integral of the absolute value of the function from a to b. So I mean, like looking at this one right here, instead of actually trying to graph anything and figure out anything whatsoever, when I see area, I know that I need to talk about only positives. I'm talking about the integral from -2 to 2 of the magnitude of x squared sine of 3x dx. Then I just type that in my calculator and get an answer. The reason why I know I'm using a calculator here is because I have trig functions on an interval with integers. From -2 to 2 of the absolute value of x squared sine of 3x dx. I was really thinking there for a second. Approximately 3.684. All right, I believe that was the last of what we had to do. That was, I believe, last. Again, there's how you can do it with a calculator, just slapping an absolute value on there. There's some practice problems for you. I'll see you guys tomorrow.